SQL as before, and right now we are going to listen to a very interesting presentation by Alexander Korotkov, who is the founder of Postgres Professional and one of Postgres community committers. And let's get started. Thank you so much. Hello everyone. My name is Alexander Korotkov. I am Postgres committer from Postgres Professional Company, and my today's presentation is about Postgres bottlenecks. And I would like to start with a short disclaimer that I don't bear any responsibility on your expectations from my presentation. Of course, I will be talking not only about all bottlenecks, but just about a few of them that I have encountered in my experience, and I just have to talk about it. The presentation will look like a set of use cases. Of course, I can't just get all these new use cases and show it to you, so I decided to replicate these problems in Postgres using PGBench with some custom tools. You can come up with very interesting things. Also, I will have some evaluations whether it's good or bad, but of course if you are not assessing right now using words like good or bad, it will be like normal, it will be very average. Okay, let's get started, and my first example is about workload with intensive update. Let's say we have a table with URLs. URL has a link, a number of parameters, indexes with them, and a column with the number of hits. What we do with this? Periodically we increment hits. For example, user goes to a website, we increment those hits, and it's like this. By using PGBench, it can be represented like this. We write a custom script, we take URL ID randomly, and then we write a trivial update. On Amazon virtual machine with 72 vCPU, we start PGBench and we get around 200,000 TPS with around 2 megabytes per second of writes. Everything is okay. Let's say we didn't require 200,000 TPS, but we required 100,000 TPS, but that's okay. We have some buffer, and in production we see the following. If we take a random zip file and we call PGBench, we see that TPS is not 200,000 but 1500, which is around 10 times lower, and the speed of writes is around 5 megs per second. So on one hand the figures are lower, but if we calculate how much we spend per transaction, still it's 5 times higher. But what happened? Why everything was good before, and then with random zip file everything was bad? Unequal distribution happened, and we have encountered very high competition over strings, over rows, and they encounter logs. And the next thing, maybe not very clear, that hot equipment started to work less intensively. So the first problem, more in detail, how in Postgres log is operating when we update a certain tuple. The thing is, tuple has TID, a physical location identifier, a page and a deviation. If a lot of processes are fighting for one tuple, a lock is created in a memory, and this lock is associated with TID, and they are standing in a line to get this TID. But what happens next? A new version of tuple is created with a new TID, and those trying to update, they still become just one less. They are building a new line for the new TID. And finally, we come up with this problem when actually they go from one TID to another TID, which is very bad. And the right solution to it is to apply a patch written by Konstantin Knizhnik, if I'm not mistaken. The thing is, we associate lock not with TID, but with primary key, not with physical location of tuples. And this primary key never changes. We have one key, and all processes go one by updating this string. But this patch, it was published, but it still has some problems, and we didn't touch it for quite a while. But as long as I am a committer, maybe one day I will fix it. Second thing about hot. In Postgres, tuples are stored in a heap, in a flat structure with links from index. If we don't have any index spaces updated, then index can stop updating and only heap will be updated. And in heap, hot chain structures are created. So we find this hot chain and then we choose the right tuple. Seems like everything is okay, but it's better than when we have loops, equal loops. So when we go to a page, most probably we will find some room to put a new tuple. But if the distribution is with displacement and we update the same row, it happens that the pages is overflows, the hot stops, and then regular updates come over and they update indexes, and it happens that these unequal distribution are bad for hot too. What workaround can be implemented? We can make something like this. Have a standalone table with hits, with just two fields, ID and hits, and you won't have to update so many indexes. With PGBench, we can run the same test and we see that TPS grew, of course not to 200,000 TPS, but around by two times. And the write speed is around 4 megs per second. Well, it's still 3 times better, and it's a very good workaround. So to wrap it up, of course you need to run a load test on different days, and in real life these unequal distribution are very different, and you need to find the worst case for you and to focus on it. In that case, you will be right, because in real life you won't encounter the worst case, but maybe you will see problems that you couldn't even imagine, and with unequal distribution you may face high competition over rows, and also hot works worse. And for all this you need to be ready.
The next example, problems that appear with shared buffers. There's a live case. We got a lot of useless tables, and so DBA decided to delete them. Just, about 10 or 1500 tables. So we started deleting them, but actually it deletes too slow from the master. So let's actually use 20 or 30 parallel delete. So master deleted everything, but something happened terrible with the replica. Replication lag started growing linear, and replica was not actually changing or moving anywhere. In order to understand why this thing happened, we need to check the way shared buffer is structured and architectured. Shared buffer is the key table with a buffer tag key that identifies completely the block of data. Shared buffer actually indicates what type of table, number of blocks, and plus, in addition, the shared buffer says that from 1 by 1 we actually go and select the right buffer tag. We select the right hash packet, cake bucket, we go to the right bucket and find the right place. But the problem is if we need to find all the buffer of specific table and we need to purge them, then we get a really huge shared buffer task. But as you know, there are a lot of memory on the series shared buffers, also a lot, and it may take quite a lot of time. So the nearest bright future of the shared buffer looks something like this, where we just take and go away from the flat gig table and actually get to the radix tree. This will be the tree of tree. Initially, we're going to have the top level tree that matches relational with buffer, and at the bottom layer, we will have the trees that are produced by different blocks. In this tree, the search will actually n small and n big logarithm. N small is just the number of buffers in specific table. It looks like we just switched from the better to the worse, from 1 to logarithm, but here we have the benefit. In this structure, we're going to have the locality. The buffers that are located nearby will be stored in our structure nearby, and it means that it's a good and positive thing. But it isn't the case in all the time. So the great advantage that the search of all the buffers in all the table will be n capital and n small one. We find the subtree and we purge this subtree. Andres Foreman is promising us this future, and he's been promising for about 3 years, but patch is not there yet, and nobody else has been trying to do this. In Postgres 12, we committed a small facilitation. If we take and make a drop table command in one transaction and make it several tables, then in Replica they will be purged in one pass, in one transaction. And if we take and instead of actually throw the table one by one, if we do it this transaction, it means that the replica may survive. The resume is simple. Postgres is quite difficult to scan sequentially the replicas. We do it in one thread. And fortunately, we have some cases when we can optimize it. And in practice, DBAs are doing smaller shared buffers on this replica, and replica is able to take it. Next example, disappointments that happen with Safepoints. I'm talking about the cases when we have a great number of Safepoints. Here we're going to go all the way to the source code. It's the real ad hoc case. Just imagine we have the script like this. When we make an insert one by one, and we have a lot of Safepoints. We get a Safepoint after every insert, and only then we commit only after this. So this enables us to copy rows as many Safepoints as we want. So we launch it as follows. We take the script that generates Safepoints in 2 threads, and we take separately a script with the daily load. It will look the way the performance will actually change depending on the number of Safepoints on script 1. And here we have an interesting thing. Here we have a degradation, a smooth degradation, and then all of a sudden, when we get from 60 to 65 save points, we get a significant 4-time performance drop. It's an unexpected behavior if you don't look into the code. It's not quite obvious the reason it happened this way without looking into source code. Let's check the reason it happened this way. In Postgres, in the shared memory, every process has a structure that when we actually make a save point, we create a subtransaction with its own ID. So there is a structure in the shared memory that for every transaction allocates 64 ID of subtransactions. Then we ask ourselves, when we actually fall within this limit, then it's okay. But how does it work if we fall outside the limit? If we're outside the limit, there is a magic flag called overflowed, and it is set to true. And if one current transaction is overflowed, then the whole snapshot becomes overflowed. And what happens with the overflowed snapshot? Now, when we check the visibility, we cannot just simply tell whether we see it or not. We need actually to get whether this ID is the ID of another subtransactions, and if this is the subtransaction, the parent transaction is stored in this special data structure. Please watch out. Remember, when you actually do the truncate in the SQL, it also happens in the endpoint. So what has in the transbench is like an artificial, but if you look at SQL, it just generates over 64 subtransactions. It happens in a very easy way. It is stored in this specific structure. So, on the slide we have the technical information. Probably it's not that important, but the thing is, the structure of data for a small number of buffer, no more than 128. Then we are just looking for the buffer sequentially, and actually we'll spend some time trying to identify what subtransactions, and how they are related. We're talking logs are not very well differentiated. Initially, commit, don't treat this. If you go through the slides, you'll be able to find and go through the code by commit hash. So this is a log where we actually commit transaction. Then we got a separate standalone structure. Very simple. That should work faster than buffer manager. At the load, all that time. And it used to work faster than buffer manager back then, considering the back then load. Then we extrapolated it to other data structures, including transactions and subtransactions. But we got the following. It means that in many workloads it works terrible. And what shall we do then? The first thing that a standard user shall do doesn't create more than 64 save points, then everything will be okay. Second thing is you can go in the code, the way this macros looks like. You can recompile it and continue using it up to 128 save points, and you can actually repeat this operation. You can add up RAM to your server. You can also wait till that heap is published, or any other storage based on undo. Store undo based storage shall not be taken. You do not need to create any other skid. You can actually remember the position you want to log and revert back to them. I have another idea how you can find workaround. If you come to Postgres Pro and pay a lot, we will make a special distributive for you with a workaround. Yet another community promoted subject. It is not related to this case of 100%, but actually we need to get rid of SLRU, and get to the buffer manager. So Amazon is saying that they're going to make the patch. They actually published Aurora, and they reworked the disk access layer. They didn't really like SLRU. They removed it and replaced it with something else. They promised to issue a patch, but haven't sent anything over one here. There is yet another case. Very terrible update for Postgres. It's just the most terrible Postgres you can write. You can actually take and write. You could take and write all the columns in the update, even those you don't change. But Postgres doesn't check that you haven't changed the cell. And if you actually write like this way, then hard will not work. And unfortunately, as far as I know, they do it this way. They don't check whether you change the field or not. They just check it and generate the update that actually takes and rewrites all the columns. You can measure the estimated effect on when we make this type of update instead of normal one. If we take this type of update and let's actually force it to make the empty update for the bit field, and actually we make the index search, you can actually model the real situation. And the difference is immense. If we take and make a stupid update, as the hard is not working, if we don't just write the column, we get the 115,000 TPS. The moral is the same. So if you don't update, just include them. So you can actually add up a storage, even if the storage will do an additional select, it will actually be a win situation. Let's think about yet another example, how row level logs are not really free. Well, it will seem what happens if I write select and make for share. The slide is not correct. So if we're just taking this, it just gives 620,000 TPS. And if we make select for share, that locks the field below the row, then the performance will drop 5 times. What is the reason? The reason is simple. The Postgres has the mechanism called multi-exact. It is needed if the transactions that are related to this row, if the count of this transaction more than one, it has the field called xmax. You can identify one transaction ID, and as you know, when we do for share, it's not an exclusive lock, and it means that several transactions may block for share. Then Postgres creates a new multi-exact. This is an ID that is responsible to notify that this row with this multi-exact lock is blocked by these two transactions, and so you can easily find the transaction that locked this row. And it is implemented in a very primitive way. There is a separate structure with offset. There is yet another sit with the members. Two transactions locked one row. We just take in member and we add 2 digit. Then we go to offset and add a link to where we stopped writing members to. And there is no unique ID verification. Every time we just add up new records there. So it turns out to be that in our case, when the transactions overlap with each other, make lock for sure, then they just take these multi-execs and generate them in a very large flow. That's why per second I got 24,000 multi-execs generated per second, and on average 2 offsets per 1 offset. That means that on average we had 2 transactions locked one row. So how can we get rid of decisions? There is a bypass. You can actually take and get from the advisory lock. Advisory lock is the lock that is stored in the operating memory. And you can easily see that if we take and instead of making select for share, we make advisory lock, then the performance will be 290,000 TPS. That means just 2 times lower than if we would actually go without any lock. So in principle we have a question. Why don't we have a mechanism that stores locks in memory and all the time? Why do we make some type of records? The reason is very simple. If we store locks in memory, then we have a limited number of memory, especially the shared memory. And to bluff, we can actually lock an unlimited number. Postgres is the mechanism that the logs where we do to double is written to the disk. But if we know that in our specific workload we will not have too many locks we need, we actually can take and change the advisory with locks, and we're going to actually have the painless operation. The resume is as follows. If you take a lot of row level shared locks, then you have a risk that the multi-execs will get too many, and multi-execs are written to the disk, and this is an additional disk load. And the bypass in the form of advisory lock can help you. So that was all examples I wanted to share with you. So actually I spent less than 30 minutes, and I do hope that these examples will help at least some of you, will save some of you from an unthought or unwise decisions, so that you will not use anything not working for production. Thank you very much, and I'm ready to answer your questions. Good afternoon. Is it possible to diagnose this process? Because this is a related situation when we know what we check. But when we are in production, all of a sudden everything slows down. How do you know where to look for? Is there any way to identify these problems? Yeah, probably this is missing in my presentation. I agree with this. As for the multi-execs, you can actually use system functions. You can get the number of the current multi-exec offset and member. And in this case, you can monitor the number, how many of them are generated. And you get the idea that we have the problem that we generate too many multi-execs. Probably I will just tell you something about diagnosis. As for how often we use the hot, I don't remember whether we have statistics in the system. Yes, we have. So you need to monitor the hot use frequency, and if you see that the index column are not updated but hot is used, very rare, so it's the reason to think about it. So it's just save points. I don't know whether Postgres has any type of metrics to monitor save points and their count. Possibly we don't have anything to monitor this in Postgres. So what can we do? You can take Postgres debug and see with perf. And you can check it at the level of operating system because we look into the trans directory too often. It's like an indirect way to check the situation. So, and if Replica gets stuck at share buffers, you can understand this by launching perf. I don't know how else you can tell that it's stuck. GDB, perf, our favorite tools that any DBA, Postgres DBA shall be good at. And as for the first problem, you monitor hot and you monitor PG logs. If your transactions are in log tuple, you will just see it on PG logs. It is the easiest thing to see. I think I answered your question. Okay, let's continue.
Почему вы
Tell me please, why did you say that advisory logs is just a workaround? How can we use them properly not to call them a temporary solution? In this claim you said about your own opinion. Well, it's not just a bypass or temporary solution, but out of all things that we can use right now, raw logs from user's point of view, it would be reasonable to expect that they would be operating normally with no significant performance degradation. So in that case, advisory log is a bypass, but in fact it's a valid solution to a problem. It doesn't have any significant drawbacks or side effects, but the way we reach it, it looks like a bypass. Did I get it right that advisory log works only against those procedures that will check it? Yes, of course. So you will have to put it everywhere. Unlike the original for share. That is why it is a bypass. Well, once again we find ourselves in the area where there is no common opinion whether it's a bypass or not. Well, for example, serializable is a legal feature, but there are some transactions that use it, some that do not use it. So if all your transactions are using it, that's okay. If not, it will get your high-level logic on this serializable and just break it down. So this is the way how it should work. I would like to ask why, while dropping a table, blocks are being cleaned up from shared buffer in order not to push them away, but it's good because they're like orphanage and they will be pushed away. It's at some time. First you need to make it happen. You have to give up from showing error when we push away a block or a buffer and we don't see a block in there. By doing so, we are losing our capability to identify errors. But what kind of error are you talking about? Well, IO go somewhere like antivirus was installed on a PC and deleted the relational file. Now, BG writers checkpoints believe that if they find something in shared buffers, they can write it. If we now we need to teach PG writers and checkpoints that they need to survive the situation when a file does not exist at all, or we need to go to a page and see whether this page exists, and also we need to stop the transaction that is going to drop it. But in order to keep this stable, we put this transaction to a disk. But in that case, we will be facing problems with concurrent interaction. Well, it's like something is being written and we decided to drop a table. And another problem is that in Postgres, that 32 bits OIDs are being modified, and the risk is that a table with the same OID will be created and it will inherit those buffers from the previous table, but it's like my own assumption. Thank you for your presentation. My question is about replication and tables drop down. So is it typical for all types of replication? Does it apply? Is it applied to binary log? We don't have a binary log, but we have logical replication. Yes, it can be applied to it too. I don't know at what stage they are with BDL replication, but the fact that we are replicating DDL and we replicate drop table, and for Replica it will do the same. It will take the tables and drop it. So apart from cutting costs for buffers cleanup, only parallelism will work. So on master we can take and launch a parallel thread, and in Replica we can't do it. So it's a common problem for all types of replication. Yes, okay, got it, thank you. You're welcome. So logically, maybe it's not the case because it doesn't support drop tables, but when it starts, you will see. Okay. Any more questions? Here, yeah, young man with his hand. Not a question. First of all, thank you so much for your presentation. I'm surprised if a column didn't change and the value didn't change and we are not using hot, how to compare two values? Why don't you compare two values, or there are some maybe some moments that are invisible because you just spent 30 minutes to write a patch. So in fact we had a patch not like this, but it was required for situations like this. We updated a column, but we have an expression index for this column and it didn't change. For example, we have JSON, we changed a field, but the index was for another field and the index didn't change. We wrote this patch and even committed it, but then we found a lot of architectural problems and decided to revert it and even back-patched in last release. Well, it would be great to do it, But in fact, it's not that trivial as it may seem. You can write it in a very simple way, but community will not accept it in terms of architecture. And also, the high cost will happen when you compare two states. It can be cheap if we write some and full, but in Postgres we support custom types. And first, that custom type may not have an equality at all, and if it is the case, we can't compare anything. And secondly, the equality can be not that cheap as we expected. In this case, maybe you don't know it, but Russian language is very specific. For example, in UTF, letters like yo and yi can be written in different ways. So in coding, it didn't change. So you can write it with a standalone letter or a letter with umlaut. And in certain cases, it is bothering a lot. So when you compare it, you have to bear these things in mind, although they are not quite visible and clear. So sorting in B3 and what we are talking right now are quite different. So I wanted to say the same thing as further did. So for example, Postgres simple type text, when they compare strings, they just use MP. And when they makes more or less, they will use locale. And if we take CI text, so during comparing, they will be doing some very weird things like trying to arrange the register with local settings. So if you don't have a real HUD and you don't have to compare, so this check is unnecessary, it can be very significant in terms of performance. So maybe you will require a certain option, not like you are comparing everything. Maybe you can just give your user an option to disable this comparison. It's a very good example with CI text. So a bug can happen if, for example, we call operation with equal and it works without case, without small or big letters. And you will see that the values are equal, but you change catalyzation. So it will assume that there is no need to change index. So whether you are using sequence scan or index scan, the capitalization will be different because index didn't change. So the conclusion is that during update you don't have to pay attention to these comparison operations and use just CMP. It will protect us and it will be faster. Alright, I think we need to give the floor to other guys if they have something to say. If no, let me say a huge thank you. We made it in terms of time frames. Thank you so much and see you later.